Good afternoon or evening, I guess, as we're approaching. First, I just want to say thanks to Manas for paving the way for me coming into this room, and for Deepak and Carolyn for bringing me on stage. Lots of stuff to cover, but we'll do it quickly and efficiently. First, a few disclosures, my points of view. I'm a liver pathologist. So the I ams Alyssa was talking about. I'm a liver pathologist, which means I spend hours every day looking at people's slides under the microscope, which means I really spend my day at two levels of scale. And you'll see how that plays into what I'm going to try to unfold for you. I also do adult stem cell research, and that was my entry point into talking about the kinds of things I'm going to talk to you about. I'm obviously not going to go into that in detail, but my team, along with several other teams, did work about 10 to 12 years ago showing that adult stem cells could do everything embryonic stem cells could do. It was that work that led to George Bush's address to the nation, et cetera. And that topic is what won the Nobel Prize last year. But it was the technologies of how to make that happen in a culture dish that won the prize. So it's sort of accepted now that at least at some level that happens. But what we were showing is that this is happening in our bodies all the time. And then because of that, I became a student of complexity theory. That's a separate story I don't have time for. And I also have to say that I'm a 25-year Zen student at the Village Zendo in New York. And that feeds into some of how I both do science in terms of how I contemplate questions and find answers. As was being discussed before, it's very rarely just a straightforward intellectual process, but also some of the other stuff I'll unpack for you. And I guess at the Planck level, I'm a nice Jewish boy, but I didn't put that on the slide. Okay, so complexity theory. This is a quick, it's about complexity, but it isn't actually very complex. So complex systems are groups of interacting individuals that, if they fulfill four criteria, organize themselves from the bottom up into larger scale structures. They appear planned from the top downward. Intelligent design. But they're not. And these structures that emerge from the bottom up are referred to as emergent self-organization. You've heard the word emergence pop up in a couple of other places. I would agree that I don't think of consciousness as an emergent property, although that is one argument which I'll get to in the middle of the talk. And the key thing is that they're adaptive. So a complex system can change how it self-organizes if the environment around it is changing as well. So it can adapt. This has been used to describe rise and fall of economic markets. It's a dominant model for how to talk about economies. If you're familiar with the work of Jane Jacobs, she was talking about cities as complex systems of interacting citizens long before there was a language of complexity theory. Immune systems was a place that was talked about in biology. We brought the discourse into stem cells. Beatlemania is my favorite example. Ask me about that later. What are these four criteria? What makes a group of interacting individuals able to self-organize? Number one, there have to be a lot of them. And how many you have, if you have more, it increases the level of complexity. So 3 ants don't make an ant colony. 25 do. If you get one of those little ant colonies from the comic books or from the internet, 25 ants will do it. And they'll make food lines and dig tunnels and build cemeteries. If you have 2,500 ants, it's a more complex ant colony. 250,000 ants, still more complex. So a village is not a city, is not a megalopolis. There have to be an overall balance of negative feedback loops in the system. So think an air conditioner thermostat. Temperature in the room rises, air conditioner turns on. Temperature goes down, air conditioner turns off. So it stays within a homeostatic boundary. You can have positive feedback loops, so the warmer a room gets, the heat turns on and it gets still warmer and still warmer. But if those predominate, you either don't get self-organization, or if you do, it's not adaptive anymore, it's energy expending. So think hurricanes, tornadoes, cancer. Interactions are local without global sensing. There's no ant in the colony that's worrying about whether there's enough food or whether there's an ant colony next door that's going to be a challenge. They're just paying attention to what's going on in the local environment. And then there has to be, this is the niftiest thing, there has to be low-level randomness in the system. If there's too much randomness, you just get disorder. You don't get any self-organization. But if you have too little randomness, then if the environment changes, the complex system can't find new ways to self-organize, to adapt. So that low level of randomness, and I think this is in part what you guys were talking about in terms of evolution, it's not randomness in terms of mutations, it's quenched disorder of the system. So a low level of randomness is what's key. So if you have a food line of ants, it looks like a straight line. But if you bend down and look more closely, there's always 3 to 5% of the ants that aren't following the line. It's these ants that are likely to find a new food source if the old food source runs out. Or if you put your foot down in the middle of the line and interrupt it, it's these ants that will very rapidly find the quickest route around your foot. So the quenched disorder in the system is what provides the ability to adapt. And this was brought to my attention by a colleague, Jane Prophet, who's an artist, who said, this is the kind of thing you're talking about with your stem cells. These cell lineages, which historically we say go from embryonic stem cell to adult cell, or from liver cell to more differentiated liver cell. But then in our experiments and several other groups about a decade ago, we were showing that there was this low-level engraftment, stem cells injected into the circulation from one animal into another. And we saw this in humans too. 1%, 1 in 1,000 cells were deriving from the circulation. And this led us to a series of papers that said low-level engraftment of circulating stem cells into varied tissues is not only not trivial, which was a critique when people were trying to protect embryonic stem cells. They were like, well, adult cells, they're not really doing it, and even if they are, it's so rare. That's the point. It's not only not trivial, but it is vital. Literally so. This is how cells self-organize into the tissues and organs of our bodies and accomplish repair when repair needs to happen. Now, an implication of thinking of cells as a complex system is the necessity of there being mass extinction events. This is not a real phase diagram. It's kind of a fake one, but it works. So if you consider the ways things can be in a system, you can have total disorder, complete randomness like in a gas, total order, completely predictable like billiard balls, or fractal chaos. And it turns out that mathematically, complex systems lie at the edge of fractal chaos. So one way of referring to this frequently is life at the edge of chaos. That's a common phrase you might hear. Now, you might think then you could plot any specific complex system somewhere within that zone. But because of the randomness, it's not going to be located at a specific spot. It's actually going to wander around in the zone. And given enough time, inevitably, it's going to stumble out of that zone, and when it does, you're going to have a mass extinction event. So cells self-organizing into tissues and bodies means that there's eventually going to be a mass extinction event, and an implication of that is the price of being alive and adaptive means you're going to die. There's no such thing as a fountain of youth. There's no such thing as eternal life. The two are flip sides of the same coin. Manas would say, oh, another complementarity. The universe is a complex system. And this is, I think, where Deepak's interest comes in. You can think of complex systems now in hierarchies. We've already done that implicitly. Let's make it explicit. From a distance, an ant colony looks like a solid shape on the ground, although maybe it's moving around. When you go in more closely, you see it's not a thing at all. It's not a shape. It's a phenomenon arising from the ants interacting. Well, if you go down to the microscopic level, then the ants themselves, their bodies disappear and become phenomena arising from interacting cells. So all of your bodies you can think of as colonies of cells. You have, estimates 4 trillion cells in your body are yours with your genetic information, your human cells, and 100 times that are the bacteria without which you couldn't live, covering the surface of your skin, lining the surface of your digestive tract. So you're a colony of cells, only 1% of which are human. So whether something appears to be a thing, as opposed to a phenomenon arising from smaller things, depends on the scale of observation. So here's an example. I was in Rome with my husband a few years ago and heard a noise overhead and saw this. These are flocks of starlings migrating from Central Europe to North Africa. But it looks like a solid thing in the sky. But you know it's not a solid thing at all. It's just a flock of birds. Just as my finger pointing at the flock of birds is really a flock of cells, self-organizing into something that looks to you at this level of scale like a finger. So this is an example of what Manas was referring to as complementarity, and we've published on this topic. that whether something appears as a thing or a phenomenon depends at the level of scale. It is not one or the other, it's both, but you're always selecting your point of view and so making a determination of what you're going to see. Another way to diagram this is cells self-organize into bodies, which organize into communities, and depending on where you draw the boundaries around what you consider a body, you can think about cities, cultures, ecosystems, Gaia, the entire planet, as a living organism. But what about cells? Are they an indivisible building block? Well, you can argue that they're just self-organizing biomolecules afloat in water. And where are biomolecules coming from? Are they fundamental? Obviously not. They're atoms which have self-organized into larger molecular structures. What about atoms? Well, they're just subatomic particles which have self-organized, and those are smaller subatomic particles which have self-organized. And now we're down into what we heard about before from a few speakers, the Planck level, where you have the smallest things. And whether those are strings or something else, they don't divide into something smaller. They simply pop in and out of the vacuum as virtual particles, most of which will self-annihilate matter-antimatter pairings, but some of them will escape that and start to self-organize upwards into larger scale structures. And that's referred to as the quantum foam. That's one of my favorite phrases I bumped into on this journey. So we don't live in the universe. The universe isn't an empty box. It's not a location in which we reside. We are actually arising from the universe. We are the universe, which has self-organized itself into this level of diversity. Though at a different level of scale from the Planck level, it in fact is one seamless continuum. You can take this in lots of different directions. We've got a couple of papers, the latest one again with Menas, where all the quantum weirdness stuff you read about in quantum physics is present in biology because of the nature of complex systems. Buddhist metaphysics, as a Zen student, this is one of my favorite things. So the idea that thingness is dependent on scale is really another way of saying emptiness of inherent existence. Inevitable mass extinction events is impermanence. That systems depend on every member and how every member interacts with every other member, that's interdependence. And the fact that if a system fulfills all the criteria to self-organize, you know it will, but you can't predict exactly what the nature of the self-organization will be. That's the fact of emergence is predictable, but its nature is not. That's karmic law. So this way of modeling the universe can give us the entirety of Buddhist metaphysics, basically, from a very traditional 21st century scientific point of view. Hindu and Jewish mysticisms, I'll just touch on these very quickly. So this is the kind of diagram I've already shown you, the generative vacuum turning into whatever the smallest things are in the quantum foam, which self-assemble into atoms, molecules, larger scale structures. In Vedantic, Vedic literature, we would talk about Ishvara and Brahman. In Jewish mysticism, we have exactly the same thing in Lurianic Kabbalah, and the Hebrew words actually map directly to the sorts of processes we're talking about at the different levels of scale. And so one of the things this solves is that these structures and processes solve the paradox of how what links us to the divine simultaneously is obscuring that link, which is always the weird thing in mysticisms when they're talking about the creation or emergence of the world. How is it that what connects us to the divine from which we emerge at the same time obstructs our view to see it without significant training, to say the least? So this gets us into the sentience discussion. So this is basically based on the work of Umberto Maturana and Francisco Varela, who at the time were in Chile, and they wrote this book, Autopoiesis and Cognition. If you go Google autopoietic theory, you'll get a lot about that. I'm not going to go into the details of it, but this is a primary version of how people look at complex systems, living systems, and think that consciousness emerges from them rather than being the emergent properties out of the consciousness. And they defined living systems, whether it's a single cell or a multicellular organism, as having boundaries, having processes, which is the being of the system, the activities of the system, a nervous system, which is the connection between external events and the internal processes of that living system, and communication channels between inside and outside. So an example of that, so what they said was all living systems are cognitive systems, whether it's a single cell or a multicellular organism like us. Paramecium. You have a paramecium swimming in some water, and it gets to a boundary. And then if you watch it from afar, it'll back up and keep trying until it gets past the boundary. Looks like it's thinking. What's happening is that the paramecium, when it hits the boundary, its cell membrane flattens out. That changes the structure of the calcium channels. Calcium flows out, and that sends a signal for all the cilia that allow the paramecium to swim. It backs up. And then the cell membrane goes back to its normal shape. The calcium channels close. This is a form of mind at its simplest level in living systems. And that's one of the arguments that these two guys were making. They distinguished consciousness from sense-making from sentience. They were all related phenomena, but sense-making, like, do I want to go up that sugar gradient if I'm a paramecium, or is it a toxin and I need to swim in the other direction? That would be sense-making. A good reference for this is this book, Mind and Life by Evan Thompson, who was a disciple of Varela. If the name Mind and Life sounds familiar to you, it's because Varela was one of the founders of the Mind and Life organization, neuroscientists that meet with the Dalai Lama on a regular basis. So within that, implicit, I'm going to focus on sentience for now. Sentience in this form can be defined as sensing the world outside, processing the information internally in a complex fashion, meaning what's going on inside you is a complex system as well. It's not like an air conditioner sensing the room where it will always do exactly the same thing until the thing breaks down. You never really know in a complex system just how it's going to self-organize, so you can't predict completely how any organism will behave in a given circumstance. And then once that information has been processed, including the quench disorder in the system, then there's a response. And that's what sentience is in living things. So my question is it really just living things? The whole complexity argument made me think the boundary between living and not living was maybe a false boundary. Did that apply here? So the first question then is, can biomolecules actually display sentient activity? And that's when we finally get to the sentient stuff. So it turns out, as one example, but there are many of them now, if you look at a DNA helix, the alpha helix, it's a perfect conducting wire. So the electrons that from the base pairs actually flow as electrical current. And because of the structure of the base pairs, you wind up having what are called quantum holes, little eddies where there is no flow. It turns out those are enriched in coding regions of the genome. And so if ionizing radiation, which could cause a mutation, comes in, it can be trapped by that hole, and that combination moves the radiation to a non-coding region of the genome where a mutation isn't going to cause such significant effects. So this is a biomolecule sensing the world, the radiation, processing it internally, moving it along as part of its response, and it's adaptive. It's actually a self-protective mechanism. Is it just biomolecules? Well, in all of these, notice there's something mediating things. So in a paramecium, it's the calcium ions. In our bodies, it's the cells trafficking around. In the DNA helix, it's the electrons and the way they flow in the helix. When it comes to atoms, well, these are just the electron shells. And how does one atom join to another or not? It depends on the nature of their electron shells. They sense each other, and there will be a quantum internal. There's always, and now we're in the quantum world, so you've got some quench disorder in the system by definition. And that's how atoms sense each other and can bind together to form molecules. Is it only atoms? Well, when you go down to take atoms apart, you separate the nuclei out into neutrons and protons, they're passing particles back and forth as well. And all the way down to whatever that lowest level of scale is. So there's sentience all the way through, by this definition. So to conclude, a complexity analysis of the universe as a unified, self-organizing, and emergent system reveals that the universe is sentient throughout, that sentience is inherent and universal in all the structures of existence. And this has a corollary to it. What are the minimal criteria for the smallest entities emerging from the quantum foam to be able to self-organize into the universe? Why is it that they just don't sit there? Instead, they self-assemble into this room, for example. Interactivity is what's essential, because they have to be interacting elements. Without it, self-organization could not take place. Therefore, sentience is the inescapable minimum criterion for self-assembly of the universe into larger scale structures. Sentience is, by definition, or how we might define interactivity. So that's what's necessary to get the whole thing going. including the creation of beings like us that are capable ultimately of being consciously self-aware. I'll finish just to tie back to the stuff Manas was talking about before. This is another way of diagramming this. The fact that the vacuum gives rise to the quantum foam is necessary and always happening, and they're in complementarity. The minute you have the quantum foam, that self-assembles because those elements are sentient. And that means you're up a level of scale, and you've now got another level of complementarity, which then is sentient and self-assembles into larger scale structures all the way up. And this is what we mean by recursion. And so what you define, the generative vacuum, that's what physicists might call it. They've got a bunch of words for it. But if you have a contemplative practice, or if you're reading scriptures that you have faith in that are revealing something fundamental about the world, this generative vacuum might be taken as pure awareness that we keep talking about. And so this is how awareness potentially, and this is the edge of the scientific spiritual discussion, I think, propagates through the whole system and the universe is conscious. I'll finish with one quote. The Sufi says, "This whole universe was made in order that God might know himself. The seed wished to realize what it is, what is in it, and therefore became the tree." Thank you for your attention.
Brilliant. It seems like there's no such thing as a thing.
There's no such thing as a thing.
Yeah, there's no such thing as a thing.
Yeah.
It's all the self-organization of the self as the universe.
Yeah. Yeah. There's nothing, wherever you look, there's always something beneath it until you get to the bottom. And then there's just the vacuum. So there's no there.
Thank you, Neil.
Sure. Thank you. Good afternoon, or evening, I guess, as we're approaching. First, I just want to say thanks to Manas for paving the way for me coming into this room, and for Deepak. Now that at least at some level that happens, but what we were showing is that this is happening in our bodies all the time. And then because of that, I became a student of complexity theory. That's a separate story I don't have time for. And I also have to say that I'm a 25-year Zen student at the Village Zendo in New York. And that feeds into some of how I both do science, in terms of how I contemplate questions and find answers. As was being discussed before, it's very rarely just a straightforward stem cell research. And that was my entry point into talking about the kinds of things I'm going to talk to you about. I'm obviously not going to go into that in detail. But my team, along with several other teams, did work about 10 to 12 years ago showing that adult stem cells could do everything embryonic stem cells could do. It was that work that led to George Bush's address to the nation, et cetera. And that topic is what won the Nobel Prize last year. But it was the technologies of how to make that happen in a culture dish that won the prize. But so it's sort of accepted. And Carolyn for bringing me on stage. Lots of stuff to cover, but we'll do it quickly and efficiently. First, a few disclosures, my points of view. I'm a liver pathologist. So the I ams Alyssa was talking about. I'm a liver pathologist, which means I spend hours every day looking at people's slides under the microscope, which means I really spend my day at 2 levels of scale. And you'll see how that plays into what I'm going to try to unfold for you. I also do adult intellectual process, but also some of the other stuff I'll unpack for you. And I guess at the Planck level, I'm a nice Jewish boy, but I didn't put that on the slide. Okay, so complexity theory. This is a quick, it's about complexity, but it isn't actually very complex. So complex systems are groups of interacting individuals that if they fulfill 4 criteria, organize themselves from the bottom up into larger scale structures. They appear planned from the top downward. Think, pardon